Hello and welcome back. Let's continue to look at partial fraction decomposition. And in the last video, we focused on fractions where the denominator of the fraction had distinct linear factors, meaning that when we factored q of x, the polynomial on the bottom, it would have some factors and all the factors were different. But what happens when those factors are the same, when we have repeated linear factors? So when we look at p of x over ax plus b to the nth power, we will end up needing to do the following. We will take those n factors on the bottom, and we will have a partial fraction for each power of ax plus b from 1 up to n. And this will seem like a lot, but in truth, it doesn't amount to a whole lot different for decomposing a fraction. So I think the easiest way to see exactly what's going on is to do an example. So here we have 2x divided by x times x minus 1 squared. So we want to find the partial fraction decomposition of this guy, and the first order of business is to identify what all the factors are. Well, we have one factor, which is x, and we have a repeated factor, which is x minus 1. And x minus 1 has been repeated twice. So firstly, we will have a fraction whose denominator is x. Next, we will have a fraction whose denominator is x minus 1, but there are two copies of this one. So we'll have a third fraction, one with x minus 1 on the bottom, but this guy will be x minus 1 squared. So again, we can see that we only have one factor of x, done. We have two factors of x minus 1, so we have one fraction that's x minus 1 and another fraction that's x minus 1 squared. On the top, we just have three numbers, so I'm just going to call them a, b, and c. And we are essentially all done, other than we don't know what a, b, and c are. So again, the trick here is the same trick that I did in the last video, which is I'm just going to multiply everything by this denominator here, and we will watch everything cancel out. So let's multiply both sides of the equation by x times x minus 1 squared. So this will be quite a bit, so I'll try to fit it in. So x times x minus 1 squared times the fraction on the left-hand side. I'll multiply it by the next guy. A over x plus, and then I'll multiply this by the next guy, x minus 1 squared times b over x minus 1. And then the last one, x times x minus 1 squared, c over x minus 1 squared. It all fit. So next, the reason why I'm doing all this is because all the fractions will cancel and we won't be left with any fractions anymore. So the x times x minus 1 squared will cancel with this x times x minus 1 squared. So we'll just have an x plus 2. This will be equal to, here I have a factor of x, and that'll cancel out with a factor of x. So I have an x minus 1 squared times a, plus what's left over here. So here I have an x minus 1 on the bottom, and I have two copies of x minus 1 on the top. So if I cancel one of them, I'm only left with one copy, and I can write this as x times x minus 1 times b. So again, one factor of x minus 1 cancels at the top, not both of them, so I'm still left with one there. However, in this last one, I have x minus 1 squared and x minus 1 squared. So this guy will cancel with all of that guy, and we'll be left with plus x times c. Next order of business, let's expand everything here. So we have x plus 2, x minus 1 squared if I write this out, this will be x squared minus 2x plus 1. This was just foiling this out and simplifying this, times a. Let's distribute this x inside of here. So this will be x squared minus x times b plus, well, c times x. That's as simple as I can get that. And then we'll distribute this a and this b. So I have x squared times a minus 2x times a plus 1 times a, well, that's just a, plus x squared times b minus x times b plus x times c. So this is as simple as we can get this. And again, the trick is, and maybe I'll start highlighting this in numbers. We have some terms on both sides that have x squareds in them. We have some terms that have x's in them, and we have some constant terms without any x's. So let's look at the terms without any x's first. So 2 here doesn't have an x in it. That's on the left-hand side. On the right-hand side, what terms don't have an x? We've got an a, and that's it. The a term is the only one that doesn't have an x in it. So we know this. We know that 2 has to match up with the a. Let's look at the other ones. If we erase our red lines, now let's look at all the terms with an x in them. So here's an x. That's an x squared. I'm going to ignore that for now. Here is an x. Here is an x, and here is an x. So x on this side is going to have to match all of the x terms on this side. So minus 2x times a minus x times b plus x times c, all of this is going to have to match the x on this side of the equation. The x terms must balance. We have to have the same amount of x's on the right-hand side as we do on the right, as on the left. So x is going to have to be equal to negative 2xa minus xb plus x times c. And then lastly, we have our x squared terms. So on the right-hand side, we've got an x squared and an x squared. So we have an x squared times a plus an x squared times a b. What do we have on the left-hand side? There isn't any. However, it's almost as if I have 0 times x squared. And the reason this is because I do have some x squareds on this term, so they have to add up to something. Well, if I don't see anything, it's as if there's 0 x squared on that side. So this is just going to be 0 times x squared. And again, what I'm going to do is I'm going to cancel out these x's here. So if I divide everything here by x squared, I'm left with this equation. So again, all I've done to this final equation is I've divided everything by x squared. This guy, I'm going to divide everything by x as well. So if I divide x times c by x, x is cancelled, x is cancelled. X is cancelled, but my 2 shouldn't have disappeared. And this is actually a minus sign, although it's a little bit low. And if I divide x by x, I get 1. So I have 3 equations with 3 unknowns. Luckily, the first equation is pretty simple. 2 is equal to a. I know a is 2. When I look at this bottom equation, I know that a plus b has to be 0. So if I plug in 2 is equal to a in here, I get 0 is equal to 2 plus b. So b has to be equal to negative 2. And then the last equation, maybe I'll do this down here. We have 1 is equal to negative 2 times a, which we know is 2, minus b, which we know is negative 2, plus c. Simplifying this, 1 is equal to negative 4. Negative 2 is 2 plus c. 1 is equal to negative 2 plus c. Adding 2 to both sides gives c is equal to 3. So we found all of our unknowns. A is 2, B is -2, and C is 3. Why did we do all of this work? Is so that we could decompose this fraction into 3 smaller fractions. So we know what A is, we know what B is, and we know what C is now. So let's come all the way down here and fill that in. So x plus 2 over x times x minus 1 squared is equal to, we had 2 over x plus -2 divided by x minus 1 plus 3 divided by x minus 1 squared. This is all that there is to partial fraction decomposition. I will do one more quick video with an example, but I also want to mention that one thing that we haven't seen is what happens with a fraction that has a nonlinear term on the bottom. So if I had x minus 13 divided by x squared plus 1 and x minus 4, this is not linear. So the methods that I have talked about will not apply to partial fractions with this. There are methods for dealing with this. However, I am not going to cover them now. If you are interested and are planning on going further, taking more advanced math classes than college algebra, do read ahead and look at this. It's not very complicated. It's just going a little bit beyond the scope of what I want to cover in this class.